Bismillahirrahmanirrahim. Dear students, in this week we will perform impact test on different steel samples. The basic objective of performing this experiment is to determine modulus of toughness of steel under two conditions. One is tension and the other one is bending. When we will discuss the performance and we will actually perform the experiment, we will see that how these two conditions can be developed while performing the impact test. The operators that we will be using for the performance include Charpy's impact testing machine. We have already seen Charpy's impact testing machine when we discussed the layout of mechanics of materials lab. This Charpy's impact testing machine mainly consists of a hammer whose one end is free and the other end is pivoted, so the hammer can rotate in the vertical plane. We have a lever with the help of which we give certain elevation to the lever and then we release it so that it can freely rotate in a vertical plane. And further, we need two steel samples. One steel sample with rectangular cross section will be used for impact test in bending, and the second steel sample with a circular cross section will be used for impact test in tension. So next is the related theory of this experiment. First definition in related theory is of toughness. From our discussion about tension test of hot roll deformed steel bar, we are already familiar with the basic idea of toughness. We know that the toughness is the ability of material to absorb energy in the plastic range. When we have a ductile material and we load the ductile material initially, so some initial portion of stress strain diagram is a straight line, and that portion is the elastic range of stress strain diagram. For example, if we look at this stress strain diagram, this initial portion is a straight line, and in this region the relationship between stress and strain is linear. And if we unload the specimen when the stress is within this range, then all the deformations recovered and the sample comes back to its original shape. Whereas the after this elastic limit, this point is elastic limit, the next range is plastic range that goes up to the failure of the specimen. So within this range, if we unload the specimen, then the material or the specimen does not come back to its original shape. Rather, there are some residual deformations. So this range is plastic range and this initial range is elastic range, and the ability of material to absorb energy in the plastic range is termed as toughness, and the total amount of energy per unit volume that is absorbed by the material in this range is termed as modulus of toughness. In tension test, we learned that how modulus of toughness can be determined for sustained load. The type of load that we apply in case of a tension test is a sustained load. That load is gradually applied on the specimen and it remains there. Whereas in this experiment we will be considering impact load. We will just discuss different types of loads in a short while and then you'll become more clear about this. So toughness is the ability of material to absorb energy in the plastic range, and modulus toughness is the amount of energy that is absorbed by the material. And how this modulus of toughness is determined? It is determined by the work done or energy absorbed on a unit volume of the material, as the tensile force, or in our case it will be an impact force, varies from 0 up to the failure of the specimen. The units of modulus of toughness are PSI or megapascal, depending upon the system of unit that we are using. And now different types of loads. So on the basis of the mode of application of loads, the loads can be divided into three categories. First one is static load, second is dynamic load, and the third is impact load. Now what is static load? Static load is the one that does not change its direction or location or magnitude. So its direction, location and magnitude remains fixed. For example, self weight of the structure is a static load. The self weight of the structure by itself, and as well as of any other component that is fixed on the building. Let's say there are some fixed machines, so the self weight of those machines or some furniture that is included in the static load. Next type is dynamic load. So the loads which change their magnitude, direction or location are termed as dynamic loads. And civil engineering structures are subjected to static as well as dynamic loads. The examples of dynamic loads are wind, earthquake and traffic loading. We know that at different times the direction and magnitude or intensity of the wind is different. Similarly, earthquake load, we don't know that when the earthquake will strike, so earthquake comes suddenly and its magnitude, direction is not known. Similarly, the traffic load, the traffic that is passing over a bridge or even a simple road, the direction or the magnitude of that load keeps on changing. Sometimes a two-wheeler is passing over a road, or sometimes a six-wheeler or even heavier loads are passing. Traffic is passing over the road. So these loads keep on changing their magnitude as well as location. And the third type of load is impact load, which is of our concern in this experiment. So there are three conditions for any load to be classified as impact load. That the magnitude of the load should be considerable, it should act suddenly on the structure, and it should act for a very short interval of time. So we define an impact load as a large magnitude of load applied suddenly on a structure for a very short interval of time is termed as impact load. And the examples are landing of an airplane on the runway. We know that airplane has a significant weight and it strikes the runway suddenly, and at the very next moment it is at a different position. So it's a significant load acting for a very small interval of time and acting suddenly on the structure. Similarly, an explosion is an example of impact load. Significant magnitude of load acts for suddenly and for a very short interval of time. And another common life example is passing of vehicles over expansion joints. In some of the cases, these expansion joints are not properly maintained. For example, in Gadishau Bridge, which is very close to our university, if you pass over the bridge, you will notice that there are several expansion joints which are not properly maintained. So what happens is that if you are traveling on the bridge, at the joint there is a sudden jump, the vehicle takes a sudden jump and then it collides back the bridge. Now that is a significant weight striking suddenly and for a very short interval of time. So that is also an example of impact load. So these examples shows that civil engineering structures are subjected to impact loads, and that is why it is important for us to understand the behavior of civil engineering material under the application of impact loads. So these were three different types of loads. Let's discuss the derivation for the formula of modulus of toughness. This is a free body diagram of our setup of Sharpie's impact testing machine. Now at this point, before going to the derivation, I would suggest you guys to watch the video of our performance. The videos, there are two short video clips. At this stage, I would like you to at least watch one of them, or at least part of one of them, so that you are totally familiar with the setup that we will be using, and then this diagram will be more clear to you. So we have a fork in the setup. This line with the end mass is showing the fork or hammer. So what the arrangement that we have, one end of the fork is pivoted and that end is here and other end is free. And we have a lever with the help of which we can rotate this fork. So this when we rotate the lever, the fork, the elevation of the fork increases, and at certain height the fork, a component that is attached with the fork, it collides with another component of the machine and the fork gets released, and then it has a free rotation. So what we do for both the tests, like impact test under bending and impact test under tension, for both of these tests we will be rotating the hammer twice. The first run will be a free run. In case of free run, there will be no specimen placed in the path of the hammer. I'm using both these terms interchangeably, hammer and fork, so you can use both of them for this component. So in the first run or free run, let's say if we talk about the first test, which is for bending, we will give a free run first, and in free run the hammer will rotate like this and it will attain certain height. So the energy that this fork has at this stage, we can call that as E1, and it can be calculated as mgh1. How much is h1? H1 is the total height achieved by the hammer. This height where the hammer is connected, this height is h known, and it is h naught is known, and we will let you know how much is this. And at every rotation we will note down the angle of rotation of the hammer. The scale that is connected with the instrument, it measures the angle with respect to this vertical. So the angle that will be attained in the free run, we can call that angle as theta1. And in the second run, for the bend test, what we'll do, we will place the specimen in the path of the hammer somewhere over here, and when the hammer will be rotating, the hammer will strike the specimen and the specimen will be broken, and some of the energy of the hammer will be absorbed in the specimen, so during that process of breaking the specimen. So as a result, for the second run, the hammer will achieve less height, and the energy in this case will be denoted by E2, and it can be calculated as mgh2, where m is the mass that remains the same, g is same, and h2 is the maximum height achieved by the hammer, and it is denoted here on the diagram. Now these heights h1 and h2 will be calculated using these theta measurements. We will measure this theta for the first free run and for the second run as well. So this is theta 1, this is theta 2, and if we draw a horizontal line here, this angle of the hammer in the free run with respect to horizontal is theta 1 minus 90, because this angle here is 90, and similarly the angle of hammer in case of second run with respect to horizontal is theta 2 minus 90. So using this diagram, we will try to develop a relationship of modulus of toughness. Now if you look at these energies E1 and E2, what is the difference between E1 and E2? The difference between E1 and E2 is basically the amount of energy absorbed by the specimen during the breaking of the specimen. So if we are able to calculate the difference between this E1 and E2, then that difference will tell us that how much energy is absorbed by the specimen. And as our modulus of toughness is defined as the energy absorbed by the specimen per unit volume, so we will divide that energy absorbed by the volume of the specimen, and we will get the modulus of toughness. Modulus of toughness expression is given in equation number 1, delta E over V. And what is this delta E? It is change in energy, E1 minus E2. And E1, what is E1? It's written here. E1 is mgh1 and E2 is mgh2. So delta E is mgh1 minus mgh2, and mg can be taken as common. So delta E is mg into h1 minus h2, and we can label this equation as equation number 2, where h1 is equal to h naught plus r sine of theta 1 minus 90. So this h1 this is h1, and this much portion is h naught, it is known. And if we consider a triangle here starting from this point that goes up to the this length of the fork is the hypotenuse of the triangle, and if we drop a perpendicular here, so this will be the base of the triangle. So hypotenuse, which is r is the length of the hammer, r cos of theta 1 minus 90, and if we add h naught into it, we'll get h1. So h1 is equal to h naught plus r sine of theta 1 minus 90, and from basic trigonometry we know that sine of theta 1 minus 90 is minus cos of theta 1. Similarly, h2 can be calculated as h naught plus r sine of theta 1. Oh, this is a typo here. This is not theta 1. This is theta 2. Let me correct it right now. Right. So this is theta 2. Theta 2 minus 90. And it can be reported as h naught minus r cos of theta 2. And this naught is a subscript. So let me correct that as well. Okay. H naught. So now if we plug in the expressions of h1 and h2 in equation number 2, we get delta E equal to mg into this. We have simply plugged in the expressions of h1 and h2 in equation number 2. And h2, positive h2, and this is positive h naught, and this is negative h naught. So these two will be cancelled, and r can be taken as common. So delta E comes out to be mgr into cos of theta 2 minus cos of theta 1. M is the mass of the hammer. It will be given to you. G is already known, and r is the length of the hammer. This is also known. Theta 2 and theta 1 are our observations during the performance of this experiment. So if we know this delta E, we can calculate modulus of toughness, because the volume of these specimens will also be known. These are specially prepared specimens, and we will let you know that how much is the volume of these specimens. Next is the procedure. Just very briefly, procedure is described here, but when you will see the performance video, I suggest you guys to write down the procedure in your own words for bending as well as for tension, and then you will write down your comments about this experiment. And here is the observation and calculations part. Mass of the fork or hammer, as I said, both means the same. Mass of fork is 22.9 kg. You will use the same. Radius of fork r is 0.7 meters. Volume of the specimen used in tension is 0.25 inch cube, and you can convert that into millimeter cube. And volume of the specimen used in bending is also given. Specimen and hammer combined mass. Okay, what this hammer is, in case of the performance of impact test under tension, we attach an additional component with the specimen. When you will see the performance, you will see that, and that additional component's mass is to be added into the mass of the fork, because that component is added to the fork. So in order to calculate the energy, we need to consider mass of that hammer or that additional component as well. So it's also given 0.680, and I think for your specimen it was 0.681 kg precisely. Okay, then it's the table to report observations and calculations. Test name, bending, tension, we'll be performing both of them. Height attained by the fork, initial angle, this will be measured when we will give free run to the fork, and 138 degree, 139 degrees. Final angle, it is when the specimen is placed in the path of the hammer and it fails. So these angles are also part of our observations. And then simply delta E will be calculated by using all these known values. Volumes are also known, and then you will calculate modulus of toughness using this formula. So this will complete the performance of this experiment, and these values are just given here as an example. When you will watch the video of the performance, you will observe that when we are doing that, we are giving you the values of our observations as well. So you will be using the values for your own specimens. You will not be using these values. So just be clear about that. So with this, our discussion about this experiment is concluded. Thank you very much.